Hey everyone, and welcome back for another deep dive. Today, today we're going to be looking at something called large concept models.
Okay.
This is some cutting-edge research from Meta,
Right.
and when I first saw this, I was kind of like, okay, another language model.
Yeah.
Like, what's the big deal? But as I dug into it, I realized that this is actually a really different approach. We're talking about potentially moving beyond just processing language at the word level
Mm-hmm.
and moving to something much closer to how we as humans think, which is, at the level of concepts and ideas.
That's right. Yeah. It's a pretty big paradigm shift from what we're used to with large language models.
So how would you describe the limitations of current LLMs? Even the ones that are,
Right.
really impressive right now, what are they missing?
Well, I mean, they're still pretty amazing at predicting the next word in a sequence.
Yeah.
But they tend to get stuck at that word level. They're not always grasping the bigger picture, the underlying meaning.
So it's like they're good at grammar and syntax,
Yeah.
but they don't really get the deeper meaning.
Exactly. And also that limitation becomes even more apparent when you think about languages beyond English.
Right.
I mean, most of the LLMs that we have are very much English-centric, which makes them less useful for global communication and, can potentially introduce some biases as well.
So it's like they're fluent in just one dialect of this, much larger language of human thought.
Yeah, exactly.
So how are these large concept models, or LCMs as they call them in the paper,
Yeah.
how are they changing the game?
Well, the key is that they operate on concepts,
Okay.
which you can think of as these abstract ideas, often represented by an entire sentence. So instead of predicting the next word, these models are trying to predict the next sentence,
Right.
the next thought in a meaningful way.
So they're kind of trying to build like a chain of ideas, a flow of thought, rather than just a sequence of words.
Yeah, that's a good way to put it. And this has a couple of really interesting implications.
Like what?
Well, one thing is that it makes them potentially language agnostic, so they could be trained on and applied to, many different languages, potentially hundreds of languages.
Wait, are you saying that we could have one model that can understand and generate text in, English, Mandarin, Spanish?
Theoretically, yes, that's the ultimate goal.
Wow.
And it's not even limited to just text, because they operate on concepts that could potentially be applied to other modalities like speech
Okay.
or even sign language.
That's mind-blowing.
Yeah.
So how do you actually build a model that works with concepts, though? I mean, sentences are so diverse, so complex. How do you even begin to represent those in a way that a machine can understand?
So that's where they got really clever, and they used this special sentence embedding space called Sonar,
Okay.
which supports over 200 languages and can even handle speech as input.
So I'm picturing Sonar as kind of like a giant map of concepts where each point on this map represents the meaning of a sentence, regardless of what language it was originally expressed in.
Yeah, that's a good analogy. And what's powerful about Sonar is that it's already been trained on this massive multilingual data set.
Okay.
So when you build an LCM on top of that, you're basically giving it access to this vast network of concepts.
So it's like you're giving the model this huge head start in language learning. It doesn't have to start from scratch with each new language it encounters.
Right, exactly. And then on top of that, they explore several different architectural approaches for actually building the LCMs themselves.
Okay, so let's talk about these different architectural approaches. What are some of the things they experimented with?
So one of the first things they tried was called a base LCM, which uses a transformer model.
Okay.
And instead of predicting the next word, it's trying to predict the next sentence embedding.
So it's trying to hit a moving target, basically.
Yeah.
Instead of aiming for a specific word, it's aiming for this representation of an idea.
Yeah. And it turned out that, a single context can often lead to multiple plausible continuations.
Right, because if I say the cat sat on the...
Yeah.
There are so many different possibilities of what could come next.
Exactly. So to kind of address that, they started experimenting with something called diffusion-based LCMs.
Diffusion models.
Yeah.
Like the things that power DALL-E.
Exactly.
Okay, how does that apply to language?
So it's a little tricky to explain, but imagine if you're trying to paint a picture. Instead of showing the model the full picture right away, You start with a very blurry image and then gradually add more detail.
So you're giving it hints and letting it fill in the blanks.
Exactly. And in this case, instead of pixels, we're dealing with these sentence embeddings.
Okay.
So you're kind of blurring and then sharpening the concept itself, allowing the model to explore different possibilities.
Okay.
And within the diffusion-based LCMs, they explored two main architectures,
Okay.
a one-tower and a two-tower.
Two towers. What's the difference?
So the one-tower model uses a single transformer model to predict the next clean sentence embedding, given the noisy input and the previous clean embeddings.
So it's kind of like having a reference point to filter out the noise and focus on the essential information.
Exactly. Now, the two-tower model separates the encoding of the preceding context
Okay.
from the diffusion process of the next embedding. So it's like it has two specialized models. One focuses on understanding the context, and the other one is doing this refinement of the next concept embedding.
Okay. So it's like having a team of experts working together. One group is analyzing the background information. The other group is crafting the next idea.
Yeah, a great analogy. And then they didn't stop there. They also explored this completely different approach called quantized LCMs.
Quantized. So they're turning the concept space into like these discrete units.
Yeah, exactly. So they use this technique called residual vector quantization to convert the continuous sonar embeddings into these discrete units.
Okay. So it's like they're creating a code book of concepts.
Yeah, you can think of it that way.
Wouldn't that limit the expressiveness of the model, though? If you're reducing it down to this finite set of codes.
Yeah, it's a trade-off, but it also comes with some advantages. Well, it makes the concept space much easier to model, especially when you're dealing with these large-scale models.
So you're simplifying the language of thought
Right,
without losing its essential meaning.
right. And it allows for some interesting techniques. And they explored two types of quantized models. Quant LCMD, which predicts those codebook indices directly,
Okay.
and Quant LCMC, which actually predicts a continuous target sonar vector
Got it.
that's then quantized.
Okay. So we have base LCM, one tower, and two tower diffusion LCMs. And now we have these quantized LCMs. That's a whole family of concept models.
Yeah, it is.
How do we know which one works the best?
Yeah, that's a great question.
How did they evaluate the performance of all these different architectures?
Right, so it's not just about how well these models can predict the next word.
Right.
We want to know how well they can actually capture the meaning and the structure of language at the concept level.
Yeah, you want it to be fluent, coherent. You want it to sound like it was written by a human.
Exactly. So they focus on a few key metrics. First, they looked at how well these different architectures could predict the next sentence embedding in the sonar space.
So it's like, how accurately can the model guess the next concept
Yeah.
in the sequence?
Yeah, that's a good way to think about it. But they also went beyond just simple accuracy.
Okay.
They wanted to see how well these models could generate text that was both coherent and original. So they looked at the fluency of the generated text, making sure it flowed smoothly and logically.
Yeah.
They also measured how much the models paraphrase from the context.
Because you don't want it to just regurgitate what it's already seen. You want it to be creative.
Exactly. And the results of these evaluations were quite revealing.
Okay, well, spill the beans. Which architectures came out on top?
Well, let's save that reveal for the next part of our deep dive. I don't want to spoil the surprise just yet.
You've got me hooked. I can't wait to find out what these LCMs can really do. Welcome back, everyone. So last time we were talking about these large concept models, or LCMs, and how they could completely change how AI understands and generates language. And we left off on a little bit of a cliffhanger.
Yeah.
We were about to find out which of the architectures they tested performed the best.
Right. Well, it turned out that the diffusion-based LCMs, particularly the two-tower architecture, really stood out.
Great.
They consistently produced more coherent and more nuanced text compared to the other approaches.
So this blurring and sharpening process you were talking about, where you're kind of gradually adding and removing noise from the concept embeddings, that actually seems to help the model learn these subtle relationships between ideas better.
Exactly. It's like guiding the model through that process allows it to explore the concept space more effectively and really capture those finer points of meaning.
That's pretty cool. So I'm guessing they didn't just stop there, right?
Of course not.
They wanted to push these models even further and see what they were really capable of.
Exactly. So they decided to build a much larger model, a 7 billion parameter two-tower diffusion LCM.
Wow, 7 billion parameters. That's getting into some serious territory.
Right.
What kind of data did they train this behemoth on?
They trained it on a massive data set of 2.7 trillion tokens.
Okay, so just a ton of text.
Yeah, a huge amount of text from a variety of different sources.
And all of this was pre-processed through the sonar encoder, right?
That's right. So the model wasn't just learning from raw text, it was learning from those abstract concept representations.
So it's like they pre-digested all this information for the model and created this like rich conceptual stew for it to learn from.
A great way to put it. And with this powerful 7 billion parameter model in hand, they wanted to see how it would handle some really challenging tasks.
Okay, I'm all ears. What did they throw at this language modeling champion?
So they focused on two main tasks, summarization, which we're all pretty familiar with, and something called summary expansion, which is a little bit more unusual.
Okay, summarization. I get you're kind of creating like the Cliff Notes version of a longer text,
Right.
highlighting the key points. But summary expansion, what's that all about?
Imagine you have a short, concise summary of a topic, and you want to expand that summary into a longer, more detailed explanation, but without straying too far from the original summary.
Okay, so it's like you're taking the seed of an idea
Yeah,
and you're trying to grow it into a full-fledged tree,
exactly.
making sure all the branches and leaves are connected to that original seed.
A perfect analogy. And that really requires a deep understanding of concepts and their relationships.
Yeah, because you have to be able to generate new text, creative text.
Yeah.
But it has to stay grounded in the original summary.
Exactly.
So how did this massive 7 billion parameter model do? Did it live up to the hype?
Well, it actually exceeded expectations. On summarization tasks, it performed incredibly well, even beating out some similarly sized language models that were specifically fine-tuned for summarization.
Wow, that's impressive. And to be clear, this LCM wasn't trained specifically for summarization, right?
Right. This was just an emergent capability that arose from its general training on all those concepts.
So it's like a student who can just write amazing essays without ever having taken a writing class.
Exactly.
Their understanding of the subject matter is so deep that it just flows out of them naturally.
And what's even more impressive is that the model was able to do this for languages that it had never even been trained on.
Hold on, you're saying it could summarize texts in like Spanish or Mandarin, even though it had only ever seen the English data?
That's exactly what I'm saying.
Really?
And that's because it's working with those abstract concept embeddings in the sonar space, which is multilingual by design.
So it's like, it's not tied to the specific words or the grammar of any one language.
Yeah.
It's somehow learned the deeper logic of language itself,
Right.
the underlying principles that govern how we express ideas and how we connect those ideas together.
And that ability to perform well on tasks in languages it hasn't been specifically trained for, that's called zero-shot performance.
Okay. It's one of the biggest advantages that LCMs have over traditional language models.
This is huge. We're talking about potentially breaking down language barriers in a way that we've never seen before.
Absolutely. Imagine the possibilities for communication, for education, for global collaboration.
Yeah, it's incredible. Okay, so you've totally blown my mind with this zero-shot performance. But what about summary expansion? How did the model handle that task?
It did remarkably well on that too. It was able to take those short summaries and flesh them out into much longer, more detailed explanations without losing coherence and while staying true to the original meaning.
And this is all without any kind of explicit planning mechanism, right?
That's right.
Yeah.
The model was simply predicting the next concept based on the preceding context.
Okay, now my mind is really spinning. If it can do all this without any planning, imagine what it could do if we actually gave it the ability to think ahead,
Right.
to kind of strategize like a human writer who's outlining a story or something. That's a great point, and that's actually exactly the direction that the researchers are headed in. They're realizing that incorporating some kind of explicit planning mechanism into these LCMs could unlock even greater levels of coherence and creativity.
So they want to teach these models to brainstorm, basically.
Yeah.
To create a mental roadmap before they start writing.
That's a great way to think about it. They're exploring something called a large planning concept model, or LPCM, which would work in conjunction with the LCM to generate a high-level plan that then guides the subsequent generation of concept embeddings.
So you're giving the model a blueprint,
Yeah.
a set of instructions for how to structure its thoughts and how to build a coherent narrative.
Precisely. And while the research on LPCMs is still in its very early stages, the initial results are really promising. They're finding that adding this planning component leads to more coherent and more well-structured text, especially for those longer outputs.
It's like we're taking these AI models from being talented improvisers to becoming like master strategists.
Okay.
This is all so exciting. But before we get too carried away dreaming about the future, let's take a step back for a second and acknowledge that there are some challenges that come with working in this new realm of concept-based language modeling, right?
Absolutely. Every groundbreaking technology has its own set of hurdles to overcome, and LCMs are no exception.
So what are some of the biggest challenges that they've encountered so far?
Hmm.
What are the things that could potentially hold these models back from reaching their full potential?
Well, one of the key challenges is the inherent fragility of the sonar space.
Fragility. I thought you said that sonar was supposed to be this robust representation of concepts.
Well, it is robust in many ways, but it's also very sensitive to even small changes.
Okay.
Remember, sonar represents the meaning of sentences as points in this high-dimensional space. And it turns out that even tiny shifts in the coordinates of those points can sometimes lead to really big changes in the decoded text.
So it's kind of like a delicate ecosystem where even a small disturbance can create this ripple effect throughout the whole system.
Exactly. And that makes it very challenging to train and fine-tune these LCMs because even small errors in the predicted concept embeddings can lead to nonsensical or incoherent output.
Yeah, it's like you're trying to build a house of cards in a windstorm.
Right.
You need a very steady hand and a lot of patience.
Exactly. And so to kind of address this, the researchers had to develop some really robust training methods
Okay.
and carefully curate their data to make sure that it was as clean and unambiguous as possible.
So it's like you're reinforcing the foundation of the model, making it more resilient to these little perturbations that could throw it off course.
Precisely. And then another challenge they're facing is the sheer computational cost of training and running these large-scale models.
Yeah.
LCMs require a lot of computing power, especially when you start scaling them up to billions of parameters.
Yeah, it makes sense. I mean, dealing with concepts and generating creative text from those concepts, it's a very demanding task computationally.
You're absolutely right. And so they're working on developing more efficient training algorithms and leveraging the latest advancements in hardware acceleration to try to make it more feasible to work with these massive models.
So it's this constant balancing act between pushing the boundaries of what's possible
Yeah.
and making sure that these models are actually practical to use in the real world.
Exactly. It's an incredibly exciting time to be working in this field. There's so much potential for innovation and discovery, but there are also some really significant challenges that need to be addressed.
Well said. And speaking of pushing boundaries, I'm still reeling a little bit from what you said earlier about the zero-shot performance of these models.
Yeah.
The fact that they can handle languages that they've never been explicitly trained on is just mind-blowing. Can we dive a little bit deeper into that? I think our listeners would love to hear more about how that actually works and what it could mean for the future of language and communication.
Absolutely. It's definitely one of the most exciting aspects of this whole research area. And it has the potential to completely revolutionize how we interact with information across different cultures and borders.
I'm ready when you are. Let's explore this world of zero-shot learning and all the possibilities that it holds.
Welcome back, everyone. So we're wrapping up our deep dive into these large concept models, and I have to say I'm still kind of blown away by this idea of zero-shot performance. The fact that these models can handle languages they've never even seen before.
It's really remarkable, isn't it? It opens up so many possibilities for communication and understanding across different cultures.
So how did they actually test this zero-shot capability?
Well, they took their 7 billion parameter LCM and tested it on this massive multilingual summarization dataset called XLSUM. It has text in over 40 languages.
Wow. So did this include a lot of those low-resource languages that we were talking about earlier?
Absolutely. Many of them are considered low resource, meaning there's not a lot of data available to train traditional language models. Okay, so remind me, this LCM was only trained on English data, right?
That's right.
So how did it do when faced with this multilingual challenge?
It actually did amazingly well. Across a wide range of languages, it even outperformed a similarly sized language model that had been specifically fine-tuned for multilingual tasks.
That's wild. So were there any languages that it was particularly good at, or was it pretty consistent across the board?
It was surprisingly consistent, but there were a few standouts. Like, it significantly outperformed the other model on Vietnamese, Southern Pashto, Burmese, Hausa, and even Welsh.
Wow, that's an impressive range.
Yeah.
It really does seem like these models are tapping into some kind of universal code of language.
It's a fascinating possibility. And I think the key here is that because LCMs are trained on these abstract concept embeddings in this multilingual sonar space, they're able to generalize to new languages much more effectively than traditional language models, which are, often very tied to the specific words and grammar of the languages they were trained on.
Right. So it's not just learning to translate words, it's learning to translate ideas, thought patterns.
Exactly. And that has huge implications for breaking down language barriers, making information accessible to everyone.
I mean, imagine a world where anyone can access any educational resource, read any news article, have a conversation with anyone in the world, regardless of what language they speak.
That's the dream. And while we're not quite there yet, I think LCMs represent a significant leap in that direction.
Well, this has been an incredible journey. We've covered so much ground from how these models move beyond words to work with concepts, how they can handle different languages with this amazing zero-shot performance, and how incorporating planning might make them even more powerful in the future. I feel like we're really witnessing a paradigm shift in how AI interacts with language.
I completely agree. It's a really exciting time to be working in this field, and as this technology continues to evolve, we're going to see some really transformative applications emerge. Applications that will change how we communicate, learn, and share information.
Well, thank you so much for guiding us through this deep dive into large concept models. It's given me a lot to think about.
It's been my pleasure. Always happy to share these fascinating advancements with curious minds.
And to our listeners, thank you for joining us on this exploration of the cutting edge of AI. And keep listening, because I have a feeling we'll be talking a lot more about LCMs and their impact on the world in the very near future.